there are a bunch of different ways to deal with plastic pollution. It's just, what are the trade-offs? Is it cost? Is it, CO2? What's the right answer? And there are a whole bunch of people trying to figure that out, and it's going to take a whole bunch of solutions.
Welcome to Growing Impact, a podcast by the Institutes of Energy and the Environment at Penn State. Each month, Growing Impact explores the projects of Penn State researchers who are solving some of the world's most challenging energy and environmental issues. Each project has been funded through a seed grant program that's facilitated through IEE. I'm your host, Kevin Slyman. Plastic is everywhere. It's part of our homes, our clothing, our vehicles. It wraps our food and is part of virtually every technology. It really is an amazing, versatile, and affordable material. And a highly used plastic is plastic film, as in garbage bags, grocery bags, and plastic wrap, like the very popular Saran wrap in the United States, which has been around since 1949. Generally, plastic film is a one-time use material. After that one use, it's usually thrown into a landfill, which comes to nearly 6 million tons every year. 6 million tons of plastic film. That's a lot of plastic film. Enter our team of researchers who found inspiration from a Netflix documentary. That inspiration? The amazing fungus. Now, the team is exploring if fungus could help us manage our plastic waste economically.
Okay, everyone. Well, again, thank you so much for coming and just discussing your research around plastics and fungi. This is interesting stuff, and I want to learn more about it. But before we get into it, can we go around the room and introduce ourselves?
Sure. My name is Gamini Mendes. I'm an assistant professor of plastics engineering technology and polymer engineering and science at Penn State Behrend. My background is in polymer sustainability. I've done a lot of work with sustainable biopolymers, and my core research interests is making the plastic system more sustainable, from a fundamental like structure properties relationship point of view, all the way to a systems analysis point of view. And this project really hits on kind of all of my interests. So I'm super happy that we're here talking about it.
My name's Luciana Aroni. I'm an associate teaching professor in chemistry here at Behrend. I've been here a long time. My research has been more pedagogical, just because of my position, but it's been great to be able to get back in the lab and do stuff, and working with Josephine and Gamini has been a really great time right now.
Hi, Kevin. Morning. My name is Josephine Wee. I'm an assistant professor in food science. My background is in mycology, which is the study of fungi. And my training has really allowed me to study the association between genotype and phenotype. What that means is that we're interested in genes that are in the fungi that can provide certain function for the fungi. For example, plastic degradation is one of them.
So let's dive into the problem a little bit. So plastic film, am I getting this correct? We're talking about plastic film primarily, or is it all plastics?
So the idea should work on all plastics, but plastic film is really tricky from a couple of different perspectives. One is that there's a whole lot of it. It's really light, and it's hard to recycle. So there aren't a great number of ways to economically, and that's really the key here, is economically recycle plastic film. You can do it for a couple of different things, like your grocery bags can often be recycled, but there's not a whole lot of volume. And so when we were thinking about this project, we were trying to identify really what the right vehicle for evaluating fungal degradation of plastics is. And plastic film is really probably the best vehicle because it's got very high surface area to volume. So the fungus can kind of spread out all over the plastic film and colonize it. It's really easy to kind of crumple up and really maximize that surface area. And it's a problem material, so we can attempt to solve that problem. And it's one that, consumers are going to have basically all over the world, is how do we get rid of this film in a more sustainable way? So that's really why we're looking at it.
So let's define plastic film for those of us who might be unfamiliar, or is there a definition or?
You're really talking about any really, really thin plastics. So, your grocery bags, your meat packaging, anything that's kind of thinner than a millimeter would really be considered plastic film. And you're mostly using it for its single-use packaging applications. That's where the biggest volume is going to come from. Another real tricky part that us consumers don't usually see is many of those plastic films aren't single materials. They're actually multi-layers of several different types of plastic stacked right on top of each other. And that stacking makes it basically impossible to recycle using conventional methods. And that's one thing that we're really interested in this project, is to see if we can figure out a set of different fungi that may preferentially attack those different layers and potentially, turn them into more useful materials when we're done with them.
So even though this stuff is so thin, it's actually a really complex material has different, within a millimeter, there's multiple chemistries going on within a very small amount of space.
Exactly. So some of those chemistries are going to repel water, some are going to repel fat, some are going to stop oxygen from moving through it. And so, you can't get all of those functionalities in one individual chemistry very easily. And so a lot of the industries have figured out that if we, stick a bunch of these materials right on top of each other, we can get the best properties of each, and we can drastically reduce the thickness of the material. But it means that when we're done with it, we really can't do anything with it. There's not a use for it.
Kevin, are you familiar with the history of why we have so much plastic and why we have so much plastic waste?
Educate me, please.
Dominique, please correct me if I'm wrong, but my understanding is it's a byproduct of petroleum.
Yep.
It's a byproduct of our demands for fuel. And so now we have all this material lying around. So a question that I always get is, why even make plastic to begin with, right? You would imagine that with all the science and technology that we have today, we can move away from plastics and just use material that are sustainable to begin with. However, there's this surplus from byproducts of petroleum that now we have gotten used to, right? So much plastic because of sort of this surplus in some ways from the petroleum that we're using. So it's quite the vicious cycle. You would think that plastics is plastics, but it's not. It's coming from petroleum. So it's really the whole supply chain that's an issue.
Yeah, that's definitely a part of it. Plastics are super duper cheap. Currently, the oil and gas industry is making energy feedstocks, and the plastic chemicals are kind of like a byproduct. They make money off of it, but it's not the reason that they're doing it. And so because, especially in the US, we subsidize oil and gas to make more because everyone wants to drive a car and we need to heat our houses and all that jazz. The plastics get the benefit of that subsidy. And so their price is really low. So that's definitely one thing. Plastics are super cheap. And it means that all the products that we use that are made of plastic are cheaper than the alternatives. Otherwise, they'd be using the alternative. But there are also a very unique set of properties that you can get from plastics, specifically plasticity, the fact that you can stretch the plastic a really long way before it breaks, but also things like chemical resistance, like your metals are going to corrode in a lot of circumstances, or your glasses are going to break. And so, plastics have a really interesting set of properties that you can't get from other material classes very easily or very cheaply. And so it's the trade-off between properties and costs that really cause us to use so much plastics.
So it's this question of how much do we care about what how it's impacting our world versus it's really useful and cheap. So we see that with environmental issues over and over again, right? It's this would be better for the planet or better for people's health. However, we've been doing it this way, and it's cheap and it's accessible. It's fun. We have plenty of it. how many situations do we see where that's replicated over and over again with challenges throughout our environment?
I
And
mean,
it's,
go
sorry,
ahead.
Dominic.
Go
Well,
ahead,
I was
Luciana.
just going to say, when I was thinking about this project and I was talking to people, they want to reduce their plastic use. It's just so hard. It's everything is in plastic, right? You can either get Gatorade bottles, or you can't find Gatorade bottles that are not plastic. You can have your options with soda. You could get aluminum cans and recycle those, which is great. But you've got these 2-liter bottles that are plastic. So even though people try very hard to reduce their plastic use, it's very difficult to do so.
Mhm.
Yeah. So my general impression is that we're not moving away from plastic in the anywhere close to immediate future. Just because if you tried, everything would cost so much more,
Mhm.
right? All of our systems are based around the technologies that we've kind of grown up into. And plastic is one of those. If you wanted to, kind of regress down the tech tree, and move back to a world without plastic, you'd have a whole lot less clothes. A lot of your clothes are made of plastics. Our glasses are made of plastics. All the computer stuff that we're using are enabled by plastics. And so it's not super practical to get away from plastic altogether. So from my perspective, at least, we need to figure out ways to deal with the problems that plastic is causing. And, one is waste that's going into the wrong place. So whether that's going into the water, going onto land, or just getting thrown into landfills, all of that's not ideal. And we need to figure out really the cost-effective and sustainable ways to do that. And so that's where I think, this fungi could potentially enter the picture.
Yeah, absolutely. Yeah, I agree. It doesn't seem like plastics are going away. I was just thinking as you guys were saying that, I'm like, we wouldn't even be having this conversation right now because all the equipment that we're using has at least some components that are plastic in them. So, and those of you who are listening right now, you're listening because there's some components that are made of plastic that are in the devices that you're using. So it's, yeah. So that's a great way to turn over to the next conversation, right? Or the next topic of, okay, so plastic is here. What then can we do with it? Do we know plastic film by industry at all? Is there, or is it just, it's in all industries?
I mean, it's really all over the place, because everyone's going to be using plastic for packaging. So anytime you ship something, there's going to be some sort of plastic wrap in there. So it's really industry agnostic. There'll certainly be industries that use more of it. I mean, food packaging, I think is the biggest culprit, but I mean, really everywhere. Anytime you ship something on a truck or a train or whatever, there's going to be some sort of plastic wrap in that product. So yeah, it's pretty ubiquitous.
And I think to add on to that, I just look at my own trash in my house, right? Gamni brought up this point about, it's not about recycling the plastic. It's just some of the plastics are multi-components. They're made up of multiple things, where when I'm sorting through my trash, I don't know if I'm supposed to tear this apart, separate out one of the layers and put them in the right place. So it ends up being mixed in the trash, right? I just look at my own household trash and I think about it's in every industry because I see it in my own trash when it reaches my house.
And there's this layer of chemical complexity to plastics that is way beyond, the average consumer, right? If you flip over your plastic bottles, sometimes you'll see this 1 or this 2 or this 5, and those all have different chemistries, and it means that they aren't compatible when you try and recycle them. And so if you tried to mix, say, a 1, a 2, and a 5, you'd come out with a plastic that you can't do anything with, because you've just mixed all those chemistries together and they don't play well together. And so one of the big challenges in kind of the recycling space is figuring out how to collect those materials from consumers, how to sort them. Again, economically, that's really the key here. We can sort them, but if it costs, $500 to sort a pound of plastic, you can't do it, right? And so it's really about driving down those costs and enabling good sortation. And, based on the current labeling scheme and the know-how from the consumers, that's not really happening. Currently in the US, we only recycle about 9% of plastics, which is a pretty sad number. But it's because there's a lot of confusion out there, and the economics really don't drive a lot of places to collect that plastic and try and recycle it. So it's definitely tricky.
So plastic is ending up where it's to those points, right? So we're recycling a very small percentage of actual plastic, and it's getting reused in some way, but it's a single digit number at best. Otherwise, it's going in landfills. And I pulled at least a couple stats. I think this was just plastic film. Yeah. So 5.71 million tons of plastic film is generated every year? I don't see it right in front.
Probably every year. That sounds like a reasonable number.
So that's broken down into about 1 million tons of trash bags, 1.8 million tons of bags and sacks like you would find at a grocery store, and then 2.8 million tons of plastic wrap. And it looks like 38.14 pounds of plastic film per year, per person per year.
Yeah, it's pretty crazy.
That it seems, it doesn't seem like first off, like you said earlier, I think plastic film is so light, so I can't imagine using 38 pounds of plastic wrap. That's a lot of plastic wrap.
Yeah.
A lot of volume. And then for landfill volume, it talked about 13 million cubic yards of plastic film, which ends up being 3.1 of looks like the municipal solid waste landfill.
Yeah. I mean, it's a crazy amount of material.
Once plastic goes in the landfill, or worse, out in a stream or in the forest or anywhere else, what's happening out there with plastic that's, when it ends up out in the wild? Yeah,
so there's this interesting kind of dichotomy out in the public mind. One is that plastic, lasts 200 years or 1,000 years or whatever number your source decided to pick for how long the plastic lasts, right? Regardless, it's not disappearing overnight. It's got a certain lifetime where it's relatively robust out in the world. So that's one thing. But the other thing is, there's a lot of talk recently about microplastics being generated. And if you're talking about microplastics, those have to come from somewhere, right? And I think a lot of them are coming from plastics breaking down in the environment. So one of the early studies that I looked at, when we were doing our background research for this project, was showing a lot of pitting on the surface of plastics that were floating around in the ocean. And the authors were basically saying, hey, we think that these fungi are basically eating into the sides of these plastic, pieces that are floating around. And when that plastic is breaking down, it's turning into something, right? They may be eating some of it, but there are probably also fragments of that material that are now turning into microplastics. And I think this is a mechanism of microplastic release for, plastics in the environment in general, right? When you have two pieces of plastic that hit each other in the ocean, over and over and over, they're going to abrade, they're going to break down, and you're going to fragment and make microplastics. So you've got this idea that plastics are super inert, they're super stable, they're going to last for 1,000 years, but also they're releasing microplastics and they're breaking down and they're degrading, and there's a whole bunch missing in the water column if you look at those studies. So, in my mind, there's kind of this middle ground. Plastics are kind of intractable, but also kind of active. And that level of nuance is not often captured in the literature, and it certainly isn't in the public mind. And so that's something that I'm really interested in terms of my research. Yeah, so to loop back to your actual initial question, you were talking about how they end up, what their end of life fate is. So one thing to think about is if your plastic is going into a landfill, that's kind of a form of inefficient carbon sequestration, right? So if those plastics are actually inert, and in landfill environments, they seem to be pretty inert, the carbon in the backbone of those plastics came from a fossil source, and now it's being turned into a pretty stable fossil source that's being stuck back in the ground. So kind of carbon sequestration with a bunch of extra steps. But that plastic is also a real big opportunity. So there's a group at the National Renewable Energy Lab out in Colorado that's looking at effectively the suite of uses of these plastics. And they looked at the amount of energy that's being thrown into the landfill that's embodied in these plastic backbones. And they basically found that it could power the, I think it was the entire energy use of the industrial sector in the US per year, because there's so much energy locked up into those polymer backbones. So, that means that we could use a whole lot less coal or a lot less natural gas if we use these plastics as a fuel source. And plastics are actually a really great fuel source. If you look at the chemical structure of polyethylene, which is basically these films, a lot of these films, it's gasoline. I mean, it's a solid form of gasoline. It has basically the same heat release characteristics as gasoline. So you could get a whole ton of energy out of properly, combusting these plastics. The downside of that is you lose the carbon sequestration, right? You're turning it into CO2. So, there are a bunch of different ways to deal with plastic pollution. It's just, what are the trade-offs? Is it cost? Is it, CO2? What's the right answer? And there are a whole bunch of people trying to figure that out, and it's going to take a whole bunch of solutions.
The solution your team is looking at is potentially using fungi as a solution. So tell me, how did fungus even enter the picture when it came to plastic pollution?
Everybody's laughing. Everybody's laughing because of how this originated. On Netflix, there's a documentary called Fantastic Fungi. And I like mushrooms, so I decided to watch it. And I learned it was so much more than mushrooms. It was about mycelium and spores and just how amazing fungus is. And they had a segment where there was a TED Talk where someone was talking about oil spills and having so many kiddie pools with a replicated oil spill. And they left one alone, chemically treated one, put some bacteria in one, and put some fungal spores in another. And then they just left it and came back a few weeks later. And they noticed that there was some degradation and there was some work with the chemical treatment and the bacterial, but the spores did an amazing job and the water was almost clear. And so they said that mushrooms were forming and all these, and I thought, wow, because plastics have a hydrocarbon backbone, just like petroleum products. So I thought, wouldn't it be great if these fungi could work on plastics? And wouldn't it be great if in future people could use these spores at their house in some composting thing at home and take care, be totally responsible for their plastic waste? So I went from thinking so many years down the road and not thinking of the journey to that point, but just thinking that most people would want to do that. I know very little about plastics. I'm an analytical chemist, so I don't have a lot of organic background, and I know even less about fungi. So I'm like, oh my God, what do I do? This is not something I want to give up on just because I don't know enough about either of these components. And I sent an email to our research faculty in polymer engineering, and she sent an email out, and Gamini was the one that bit. And he said, I'd be willing to do it. I'm like, great. So we met, and I said, well, okay, great. You know everything about plastics, but neither one of us knows anything about fungi. And he gave me Josephine's contact, and I contacted her and we talked about it a bit, and she was very excited about it. And that's how it happened, literally. And it sounds so silly, but I never would have envisioned this great collaboration and just the student interest and feeling good that if this works, this is a nice impact we could have. So it's kind of embarrassing how it started, but that's how it started.
It's not embarrassing at all, but it is a great anecdote. I mean, that is perfect. It's like, I don't know anything about plastic and I don't know anything about fungi, but I'm going to move forward.
I'm smart.
I need to support you.
Yes, I'm smart enough to find the people who know these things. I'm smart enough to know what I don't know. And I've learned a lot.
What it takes.
Yes,
yeah, it's definitely a skill, right? Yeah.
Excellent. Yeah, and I love the idea that this could be, I mean, in the future, this could be something that households could actually have. Imagine a household having a fungi bio recycling system in their house that the fungus takes care of it for you. Can we get into the science about fungus? Why in the world, how in the world does it even work? How does it happen? And tell me a little bit about it. Educate me on fungus and how in the world I could break down a plastic film with it.
So I think this question goes back to what Gamni mentioned about plastics, right? Two things: it's properties of the plastic, so the chemical composition, and the cost. And this is where I think fungi make an awesome candidate to solve both of those. So if you look at fungi historically, where are they found? Typically in the soil, marine environments. It's usually environments that are pretty complex. They're well-known degraders of really hard to chew on, like wood material. These are called lignocellulose. So lignocellulosic material. Their lives are dependent on rotting wood, essentially. So if you take that idea, you harness the power to be able to rot wood, which is a pretty complex carbon source. Apply that to the idea of plastics. Yes, it's a man-made product now, but I think you can take the same approach where you harness their ability to break down or chew up these complex carbon backbones, essentially. And the way they do that is through the machinery that's present in their genes. It's a group of proteins known as enzymes. There's really little mechanism of how stepwise that this happens, but we think the way it happens is through the production of these enzymes that start breaking down these complex polymers like plastics. One group of enzymes are the lacases, the same group of enzymes that are used to rot wood, essentially. Another group are known as peroxidases, which are essentially, how would you call them, Gamni? Like lipoxygenases, kind of part of.
Yeah, they oxidize hydrocarbon backbones.
Yeah. So different pathways, if you will, in the fungi that we think that can break down these plastics. I think the challenge for me is, so we identified a problem, right? There is a lot of plastics. The challenge for me is being able to replicate it in the labs, right? In the lab, I'm really limited to essentially a single substrate that I can put these fungi in. What we're noticing as we're embarking on this project is that it's hard to simulate the environment, the complex environment, let's say in the soil or in the landfill or in the marine environments, and take that into the lab. And then once you've identified these sets of conditions in the lab, to take it back to the landfills and marine. So that's what excites me the most. It seems like there's a problem. We have the science, but there's this huge gap in moving forward and also taking it back. So this feedback loop. So I think multiple things there, but getting into the science, I think we know a little bit of what we think the plastic can do to degrade, the fungi can do to degrade these plastics, but we don't know a whole lot.
And that's one of the reasons it's a seed grant, right? It's the idea that you build a foundation of information and data collecting and maybe even understanding some processes. And then hopefully you move to the next stage. You found some, there's something promising, and you can move to the next stage and maybe find, another funding source, and that wants to move it to the next level. So going back to Luciano with the oil spill in the documentary.
Yes.
What was the time span for the oil? Do you remember that by any chance?
I can't remember exactly. I think they checked it in 6-week intervals, and I just can't remember how many intervals before they saw that the water was clear.
Okay.
But that's the thing about this project, is that you think there's one question to answer or one problem, but every time you take a step towards solving that problem, 3 more pop up, or 3 more questions pop up. And so even if we get to the point where we can, find the right fungal strain and find the right environment and get this to work, the question is, how does it work? The question is, what are byproducts of this, the fungal degradation of the hydrocarbons? And so there's still so many more questions to answer that it's what makes it fun, but also kind of makes you want to pull your hair out sometimes. You can't get too far ahead of yourself, or
Right.
you'll miss the initial problem that you're looking at.
So one of the problems with plastic, as I mentioned before, is that it's kind of intractable. It's hard to do anything with, and it's because your polymers are made up of chains, and those chains are pretty tightly packed. So there's not a lot of space for other things to get in there, and the chemistry of most of your polymers is pretty darn inert. There's not a lot of functionality, especially in these low density polyethylene films. There's not a lot of chemical functionality that you can do much with. From a biological point of view, it's not something that you see a lot in nature. And so one of our fundamental hypotheses in this seed grant is if we do something to the plastic before we expose it to the fungus, if we break it down a little bit, we're actually going to be able to accelerate the rate that the fungus eats it up, chews it up, breaks it down. And so that's something that we're working on right now, is we're trying to develop methods to quickly and easily introduce these new chemistries on the surface of our plastic that make it easier for the fungus to, grab onto it and start pulling it apart.
And Kevin, to add on to your question on time, I think I look at plastic degradation from the perspective of time in two ways. One is the percent it is able to degrade. So over time, you might say, okay, so in the literature, roughly around, it ranges, but anywhere from 20 to 30 days currently. So it's a pretty long time. If you want to think about costs, one of the challenges is figuring out how to accelerate that, right? So once the thought is when we know what the fungi is doing, then we can optimize ways to accelerate that. The other thing, other than time in days, is percent degradation. Even though you say 20 to 30 days, it may be 20% degradation or 40% degradation. So it's not just the time it takes, but the efficiency of that process as well.
And kind of going back to that microplastics idea, into what is that plastic degrading, right? Are we completely turning it back into, some sort of biological carbon, right? Are we turning it completely into a mushroom or into this mycelium that we can do something with? Or are we just causing it to crumble and break down into microplastics? One of those routes is good. One of those is actually really bad. And we want to figure out, what's actually going to happen and try and engineer it so that we drive it to that conversion into biological carbon and not into a microplastic mess that makes everything worse, right? And so that's something else that we're looking at here, is trying to characterize that degradation pathway of the plastic so that we can, tailor the outcomes.
So if this proves to be effective, what are your thoughts? And I'd be interested to hear from everyone. Like, if there was a natural solution to this complex human-made plastic issue, if we could do that, what does that mean for the future, for changing, the way we operate, the hope of tomorrow? What does that mean to you if that was something that was actually an effective way to handle something like plastic?
So at least in my imagination, there are a couple of ways that we could kind of spin this out. One is as, a home plastic remedy, right? You create a little kit, you say, all right, take your plastic film, bundle it into a 5-gallon bucket, toss this powder on it, add a little bit of water, and let sit for a while, and you're going to get some mushrooms. Take those mushrooms, cook them up, eat it. Here's food for your family. That'd be really cool. There's a lot of food safety that we'd have to figure out before then, right? But I think that would be an awesome outcome. You could also look at this as a way to upcycle your plastics. So the chemistry of your fungi is going to be considerably more complicated than the plastic chemistry. And you could, develop some bioreactors to grow these fungi in a controlled way, and then harvest the plethora of complex chemistries that come out of there and create more sustainable pathways for chemical generation. Maybe that turns into, food as well. Like maybe you can feed cows with mushrooms that are grown from this at large scale. Maybe this is, pathways to new chemicals for other solutions and avoiding that kind of fossil-based pathway. But those are all really long term.
Sure.
But I think it's a good idea to have the end in mind. So that's at least what I'm imagining.
Yeah, to kind of piggyback on Gamini, I feel the same way that yes, if there's a way that you can chemically harvest what the fungi are doing, that's very helpful. The being household responsibility, but I also see it as, being by the Great Lakes here. I live in Ohio, but I still live by the lake. You see all this waste that's on the beach, and you see all this waste that's in the parks. And wouldn't it be great to go beyond the household, to have the parks and recreation systems have these opportunities to do something with that plastic waste? And to take it even further out, with businesses and schools and whatever it might be. So it can start out in your own home, but it can branch out to your community. And I think that is something that I see in my head, the same kind of chemistry going on, but on a much larger scale now. And I think that'd be wonderful. Again, many years down the road,
Sure.
and hopefully we can get there. But that's more of what I'm envisioning, just being able to know you've helped a little bit in solving a problem.
When we talk about fungi degrading plastics, there are a lot of people in engineering also working on bacteria that are degrading plastics as well. And there is a group at Michigan Tech that's working on producing protein powders from plastic using bacteria. I don't know the details of that study, but I believe it's a funded project by DARPA, Department of Defense, I think, that is, so might be worthwhile looking into that study as well with bacteria. So it's not just the fungi that are doing it. And I think this speaks to the larger question of where we have been a chemical-based economy for a long time, right? And we've realized that the chemical-based economy has created a lot of problems for us, right? It's advanced our understanding, right? It's created jobs, created our economy. It's time to, I think, transition to a more biological or bio-based economy, using the power of microorganisms, bacteria, fungi, to create solutions for us. And I think that would be more sustainable, would be safer in the long run.
So one of the big challenges here that I think is finally being realized is that the fossil fuel industry has had over 100 years to kind of optimize their process and drive down costs. And a lot of these kind of new technologies, these bio-based synthesis routes, these plastic, recycling techniques, they don't have that advantage. They can't, immediately compete on cost with the fossil fuel industry. And one thing that I've, really liked seeing from the federal government through the Department of Energy, through NSF, a bunch of these big funding sources, is that they're finally supporting basic research to identify new science and then drive that science to commercialization and effectively subsidize the acceleration of these new technologies to compete with the incumbent technologies that are based on fossil fuels. So that's something that's really exciting about being a scientist and an engineer right now, is that there's a lot of interest and there's a lot of focus on making this actually work. So I'm pretty excited to be in this field.
And I'll add to that what Gamini said. I think, to me, what's really exciting to be in this field at this moment of time is also the appreciation for this transition of basic research to applied research, right? NSF has been investing in innovation, not just in basic science, but also in applied science and commercialization. And I think being at Penn State, we have an awesome ecosystem for that, transitioning all the way from basic science to applied sciences to commercialization through our Office of Entrepreneurship and Innovation, which is nice to have.
I think that the future in this field actually looks really bright. I think there are a lot of brilliant minds looking at these problems of sustainability in our current system, not just in plastic, in fuels, in energy efficiency, and it's a really interesting time to see how the system is changing and to be a part of that change. So if there are any young listeners, we always need bright young minds to help do the research, help innovate, help figure out crazy ideas like Luciana did just by watching a Netflix documentary. And you can see how quickly you can take a crazy idea and turn it into something, operationalize it, and find funding and get some research started. So keep thinking, keep dreaming, keep imagining. There's a lot of opportunity out there to make the world a better place.
Kevin, I'll chime into that. And it's something Luciana brought up earlier about students, recruiting students to be excited about this. I think that is key here, right? I think about how we train our students for the future. This project on plastic degradation using fungi creates a really unique experience for the students. When you tell them about this project, their eyes just like light up and they get excited about a project like that. And I think this is one really tangible way to get our students who are excited about the science, they want to be scientists, and also shape them to think about sustainability, to think about how to basically decide our future for us on what we do, how we can do it, because they will be the ones taking over us. They're much smarter than we are. So I think this, from other than the science perspective, the opportunities that it provides our students, the exposure it provides our students, makes me excited as well.
Yeah, I mean, we started with one student last summer, just with a little bit of seed funding at Barron. When we brought Josephine on board, that was student number 2. In spring, we brought on student number 3. And just this last week, here, we've got student number 3 and 4 that are interested. And I think Josephine is hired.
Just hired one more. So we have a cohort of at least 10 people now that have been working and thinking about plastics, at Penn State. So that's at least fungi and plastics. So that's building a cohort that you can't build anywhere else.
Yeah, it's pretty crazy how much legs this project has gotten. But I mean, it's really interesting. It's incredibly multidisciplinary. Like, none of us could do this by ourselves, right? Yeah. And so the seed funding is really important to help encourage those types of crazy collaborations, and it's super awesome.
I think that's what's important too. We're 3 very different researchers, and yet we're collaborating on one project. And so the students that work with us see, if you're a chemistry major, you're going to be working with polymer engineers, you're going to be working with food science people, and you're never just within your own discipline. You're always going to be collaborating with somebody that knows more about part of a project than you. And I think that's a great thing to learn early on, because a lot of times people think, well, I'm a chemist, I'm just going to work in a lab and do chemistry. But depending on what your problem is, you're going to have to reach out to others and learn to work with others and learn from the others that you work with. And that's even better than sitting in a lab, by yourself.
Fantastic final words. I love it. Very inspiring, very hopeful, what a great, I love to hear that so many people are interested. I love to hear that students, it's drawing attention and interest. This project is an excellent example of how a seed grant can just really maximize all of those things. So your team is doing, in my opinion, a fantastic job. I can't wait to see more results and what your work ends up turning into. Thank you so much for spending time and talking about this. This was a great conversation. So Gamini, Josephine, Luciana, thank you so much for being here. I really appreciate it. Any parting words, anything you'd like to share, or maybe contact information? I don't know, whatever you'd like.
Thanks for having us. If you have any questions, feel free to reach out. My email is gmendis@psu.edu. I'm happy to field any questions on plastic you have. And I welcome the opportunity for more collaborations.
Thank you all.
Send all the requests to Gamini.
Yes.
I'll field them. Yeah.
Yes. Send everything to Gamini. Thank you so much.
You're very welcome. I really appreciate it. Have a great day.
Thanks, Kevin.
This has been Season 4, Episode 1 of Growing Impact. Thanks again to Gamini, Luciana, and Josephine for taking time to talk with me about their research. To read the transcript from this episode and to learn more about the research team, visit iee.psu.edu/podcast. Once you're there, you'll find previous podcast episodes, related graphics, and so much more. Join me again next month as we continue our exploration of Penn State research and its growing impact. Thanks for listening.